Welcome my friends, welcome to my next lecture. Now in my last lecture I discussed what is called power series. In fact I have introduced the notion of power series, then properties of power series I have discussed. Then most important part is that if I have a power series, then I have defined what do I mean by sum function. Then I just discussed the fact that if I have a power series, then it will have a radius of convergence. So suppose the radius of convergence is capital R, then the sum functions, if I denote it as f, then f is analytic functions which is infinitely many times differentiable. Not only that, if I take the term by term differentiation, whether first time differentiation or say kth time differentiations, then the derived power series will have same radius of convergence. Not only that, if the derived power series, if I write the sum function g, suppose after taking the kth derivative of its nth term of the given power series, then the kth derivative of the sum functions f, which is exactly equal to g. Not only that, the coefficients n I can write in terms of the derivative of the sum functions at some point. So these are the properties I have discussed. Now today's lecture, my plan is to talk about the converse of that. So that means if I have a power series, it will be an, or a sum function is an analytic functions on domain of convergence. Now if I start with an analytic functions on some domain, suppose if I take a point, say some z0 inside my domain, then f is analytic at the point z0, then can I say that, can I write my f around the point z0 in terms of power series? So that is called the Taylor series or Taylor's theorem. So my plan is to talk about Taylor's theorem and its proof and its rigorous proof in this lecture, and couple of properties later on. But I think the concept of Lorentz series maybe I will talk about in week 7, not in week 6. So my plan for today's lecture to talk about Taylor's theorem. So that means I will talk about Taylor series and the proof of Taylor's theorem. Okay, so as I said, let me just recall the kind of part to think. So these things I have already discussed in my last lecture. As I said, so in my earlier lecture, so given a power series, then its sum function is analytic and hence infinitely many times differentiable in the disk or domain of convergence of a power series that we know. Now think about the converse of the above statement. That means what questions I am interested in? I am interested in, suppose you have an open set D, suppose you consider a point z0 inside D, and suppose you have an analytic functions on that domain. So in particular it is analytic at the point z0. So now question is whether f can have a power series representations about the point z0. In other words, can I write my f of the form n z minus z0 to the power n for all z around a point z0, say with radius of with radius capital R, which is sitting inside D for some r. So that's the questions. So now I have a function f which is analytic in a domain D. I am considering a point z0 inside D. So can I write my f around a point or around a neighborhood of z0, f can I write of the form an z minus z0 to the power n, or can I have a what is called power series representations of f around the point z0 of my functions f? If I start with analytic functions and if I take z0 is point inside D. So the question is, yes, you can do that. So that is called Taylor's theorem. And then you can ask, okay, how many power series I will have around the point z0? Whether the power series representations of my functions f around the point z0, is it unique? Answer is yes, it is unique, because it follows from the fact that you can write the coefficients of your power series an in terms of the derivative of my sum functions f. That will allow you, yes, if I have a power series expansion, then it is unique. Okay, so to state that, so this is the famous mathematician Taylor. He kind of proved that theorem. So Taylor was a English mathematician best known for Taylor's theorem and Taylor's series. In fact, Taylor's series, I think you familiar with what is called in real analysis, so Taylor's theorem and Taylor series, so that same kind of mathematicians. So this Taylor's theorem is named after the mathematician Brooke Taylor, who started version of 1917 and 12. Yet an explicit expressions of the error was not provided until much later, Lagrange. Because if you remember in your real analysis, you will have like Taylor's theorem and Taylor remainder. Then there are another form of remainder that is called Lagrange form of remainder. So these are the things I am talking about. But for more information, you just go to some Wikipedia. You will have a kind of for long discussions of mathematicians Taylor. Okay, so this is the one. Analytic functions has a power series representation. So that is the statement. So what is the statement? This statement is, this is kind of converse of the earlier discussion, and that I denote it as Taylor's theorem. So what is that? So let f be analytic functions on some domain. Domain, I am having very nice domain. So it's a domain of center z0 radius r. So if my function f is analytic there, then z0 is sitting inside my domain. Then fz has a power series expansions around the point z0, and it is given by this kind of things. Okay, so fine. So therefore, if my functions f is analytic in B or z0, then fz has a power series expansion around the point z0. That means I can write my fz, which is of the form n from 0 to infinity, a n z minus z0 to the power n, for all z lies between B r of z0. And not only that, you see, I can write my coefficients n in terms of my functions f, in fact the derivative of f. So this is f n z0 divided by factorial n, but this is same as 1 by twice pi I integrations over cr fw dw divided by w minus z0 to the power n plus 1, and that you know that formula is true because you know Cauchy's integral formula for derivative, and that Cauchy's integral formula for derivative tells you the value of nth derivative of f at z0 in terms of the values of my functions f on the contour CR. What is CR? CR is the circle of center z0 radius r smaller, but it should be careful that r should be strictly less than r. That means that that circle of center z0 radius r should fully contain in my domain B r z0. This series is called the Taylor series of f around the point z0. Of course, has radius of convergence r. Look, see, I am saying that this equality valids for all z belongs to B r of z0. So that means if I take a point z from B r z0, that means if z minus z0 is r, this series converges. So therefore, at least if z belongs to B r of z0, this converges. But it might happen that this power series might converge some point z0 outside B r of z0. Inside B r of z0, it certainly converges, and it is exactly equal to your analytic functions f. But to talk about the radius of convergence, it is what is the meaning of the radius of convergence? That means you find out all those points z such that as long as mod z minus z0 is some number and there it is converges absolutely, then that is the radius of convergence. So at least I am saying that if z belongs to B r of z0, it converges absolutely. So therefore, it is certainly radius of convergence equal to r. But exact radius of convergence, even if I do not know, I can say that the radius of convergence of this power series should be greater or equal to r. So inside r, it is exactly equal to f of z. So therefore, for any z such that modulus of z minus z0 is strictly less than r, there my right hand side part series converges absolutely, and it is exactly equal to my value of the functions at z. So therefore, that means if I take z belongs to B r of z0, that means this series converges absolutely. But it might happen that if I take z outside B r of z0, that might happen because you can think about as a like independent power series, and you have no idea about the radius of convergence of that power series. So therefore, that is what I am saying, since whatever z I am considering coming from B r of z0, this series converges absolutely, and it is exactly equal to f of z. So therefore, the radius of convergence greater equal to r. Okay. So furthermore, Taylor series of f about the point, it is unique. So unique means you will say I can write my coefficients n in terms of the sum functions, and that will tell you if I have a two series expansions around the point z0, then I know my an and bn in terms of the sum functions, and that will allow you that an is equal to bn and your series is unique. Okay, maybe later on I will prove that. Okay, but let me just see if I have analytic functions on this domain, how I can get the expressions of f in terms of the power series. Okay, of course you will see that in the proof you will have Cauchy's integral formula, which will play a crucial role to conclude that theorem. Yes. So this is the proof of Taylor's theorem. Look, so now what is your domain is given? Domain, this is my domain, right? So this is my center 0, this is my capital R. Here my function is analytic, right? So what I am doing is that I am considering a small disk of radius small r. Okay, look. So this is my small r, 0 less than r. So then what I am doing is that now suppose this is my point. Okay, so this is the domain. Maybe I just remove that one, then it will be clear. Origin is not there. I think this is the z0, that is why the confusion might happen. Okay, look. So what is your center at z0, radius r. So okay. So this is, maybe you can have it this one. So this is my point z0. this is capital R, right? Then what I am doing is that I am taking a smaller open disk center at Z0 and radius a smaller, okay? And what is the boundary? Boundary I am denoting at CR. So CR is the collection of all those W such that W minus Z0 is equal to smaller, okay, right? So I have a domain B R Z0, that means I have a open unit disk center Z0 radius capital R. Inside I am considering a small open unit disk, open disk of center Z0 radius smaller is less than capital R, and this is my contour CR. So if this is the case, now I can, what is my F? F is analytic given in BR Z0, in particular it is analytic here, okay, it is analytic here. Now if I take a point Z inside CR, so this is my CR, right? So this is the boundary CR. So if I take a point, say if I take a point Z here, now you see I have a point Z here and I have a CR, this is my CR boundary, and here my function is analytic. So my function is analytic inside and on the what is called contour CR, and Z is inside CR. So then what is my Cauchy's integral formula says? Cauchy's integral formula says that I can have the value of my functions f at the point Z in terms of the values of the functions on the contour. I can write it. That's what the Cauchy's integral formula says. So therefore, since Z is any point in CR, so therefore if I take a point Z here, then by Cauchy's integral formula says that value of the functions at this point in the interior of my contour CR, I can write this value, or I can evaluate this value in terms of my values of functions on the contour. So therefore this is nothing but 1 by twice pi I integrations over CR fw divided by w minus z dw. That is by Cauchy's integral formula. But what I need what is called series expansions of my functions f around the point z0. Now I have, for any Z inside here, fz I can write in this way. So therefore what I will do, see, the idea is that, so look, in the integrand you will have fw divided by w minus z. Now w runs over CR, but z runs what? Z lies inside what is called interior of CR. So what I will do, so since I am dealing with this kind of expression, so now 1 by w minus z, I will write this object in terms of geometric series, in terms of z, okay. So I will write, or I will expand 1 by w minus z in terms of geometric series expansions, and then I will have integrations. Then, so once I have a geometric what is called expression, then I will have an infinite series, and then in the left hand side I will have integrations. So the only thing I have to do, whether I can interchange my summation and integrations or not, in what context. So that is the idea. So I will have the expression f of z in this way. I will write w minus z in as a geometric series. Then I want to just interchange integrations and summations. But that kind of, I have to give some kind of argument when I can do that. You will have if I have a power series, I already discussed, if the power series converges what is called uniformly, then I can interchange what is called integrations and summations. So that means that is uniform convergence implies. So those kind of argument, if I put it all together and if I interchange integration and summation, you will have the expressions of f in terms of the power series around the point z0. So that's the idea I have written, so in this color. So use the geometric series expansion of 1 by w minus z as a power series of in z minus z0, and then use the fact that I can interchange summation and integrations under the uniform convergence of my series fn, and then I am done. Okay, so this is the thing you have to do. So therefore first you have to apply Cauchy's integral formula, then you write the expansion of 1 by w minus z as a power series of z minus z0. You will see using geometric series expansion I can do that, and once I have infinite series and then I have integrations, then the only part is remaining how to interchange summation and integrations, and that too also follows from the uniform convergence of my infinite series. Okay, so this is the kind of idea. So let me start with that. So this is the object. In the integrand you will have fw divided by w minus z. So I just wanted to write in terms of the series expansion of z minus z0. So this is the algebra you have to do. So this object is same as 1 by w minus z0 divided by 1 by 1 minus this one. So you will see this will get cancelled. So therefore if I do some algebra, w minus z, it will go in the numerator. So w minus z, so will get cancelled. So what will remain in the denominator is that w minus z0 minus z plus z0. So this get cancelled. So we will end up with w minus z. So this is trivial. then you keep 1 by w minus z naught, because this is keep as it is, right, because I want to expand 1 by w minus z in terms of the power series of z, or in terms of the powers of z minus z naught. So therefore what I'll just fully concerned about this bracket. Now in the bracket you will see I'll have 1 by 1 minus something. So now this is a complex number. Now what is the absolute of this complex number? This is z minus z naught divided by w minus z naught, right? Now look, so now what is z? Z is interior to CR, so this is my CR, right? So w runs over CR, look, w runs over CR because of the integration, look, w is runs over CR, so w is in CR, so therefore what is w minus z naught? So this absolutely smaller, right? But what is my z? Z I am taking interior to CR. So that means the distance between z and z naught, this distance is strictly less than r. So therefore distance between z minus z naught, which is strictly less than r, which is exactly equal to w minus z naught. What it will implies? That will implies that z absolute of z minus z naught divided by w minus z naught, which is strictly less than 1. That is very important. Okay? So therefore I will have 1 by 1 minus z, or 1 by 1 minus some complex number, and what is the absolute of this complex number? This is strictly less than 1. Now once I have a 1 by 1 minus z, and if modulus of z is strictly less than 1, then you will have a geometric series expansion. I already explained that one. So this is same as sum over n from 0 to infinity z to the n. So that's exactly I will do. So this is now modulus of this fact is strictly less than 1 because of the fact that w runs over the circle of center z naught radius smaller, and z the complex number z sitting interior to the CR. So that is why absolute of z minus z naught, which is strictly less than modulus of w minus z naught, that means modulus of z minus z naught divided by w minus z naught is strictly less than 1, then I will have a geometric series expansion. So therefore I will have that series. So therefore this is 1 by w minus z naught, keep as it is. So this is z minus z naught to the power n, z minus z naught divided by w minus z naught to the power n. Okay. Then this equality I just push this what is called w minus z naught inside the summation. So therefore what I am getting is that 1 by w minus z I can write in terms of the power series, or in terms of the series expansion. What is the term? So this is n from 0 to infinity z minus z naught to the power n divided by w minus z naught to the power n plus 1. So therefore I can write the object. So keeping what is called w fixed, I can write 1 by w minus z in terms of the power series around the point z naught. Let's see, this is the coefficients, right? This is the coefficients n, because w is fixed, z naught is fixed, and this is the power series around the point z naught. So therefore first I will have the expression. Now you see, so this is the expression of 1 by w minus z, but I will have fw factor is there. So therefore later what I will do, so I will hit it with fw, then I will hit it with fw, then you will have integrand, then you will have integrand. Then question is whether these integrations I can put, or I can push these integrations inside the summations. And to talk about the, or to interchange summation and integrations, since this is a power series, I need the uniform convergence of this power series. So that is the only part is remaining. So that is why this is there. So therefore what we will have, you will have fz, which is like 1 by twice pi I keep as it is, integration CR fw, then 1 by w minus z, but 1 by w minus z just now I got the in terms of series expansions around the point z naught. That means this is z minus z naught to the power n divided by w minus z naught to the power n plus 1 dw. Then what I am doing, I am writing keep as it is, integration CR. So I am pushing this fw inside this summation. So that I can do because w is, I am keeping w fixed from in CR. So therefore because I am integration is left hand side. So therefore this is nothing but inside the summation we will have fw z minus z naught to the power n divided by w minus z naught to the power n plus 1. So then I want to change what is called summation and integrations. So I have to check that whether this power series converges uniformly if w runs over CR. So that is the only fact I have to check. So to do that, what I have to do, I will use what is called Wester same test. So that means I just take the absolute and I will say that this is dominated by some constant time r to the power n, and some r to the power n is convergent, and therefore uniform convergence is going on. So therefore I can interchange. So that's the target. So to estimate that object, since the what is called term involve what is called fw z minus z naught to the power n and w minus z naught to the power n plus 1. So for fixed w, so I have to estimate this object. Let's see whether uniform convergence is happening or not. So for to do that, what I am doing is that since W runs over CR, that means circle of center Z0 area smaller, and your function is analytic, so therefore it is continuous, and CR is a compact set, so therefore this maximum exists. So I am saying that write maximum of absolute of FW, W is in CR, which exists finitely, let it be capital M. Then if I take W is in CR, so now I want to estimate this term in the summations. So this is the nth term in the summation. So therefore if I just estimate, now you see FW, it is dominated by M because W runs over CR, so this is dominated by M. W minus Z0 to the power n plus 1, so I am just dividing into two parts. So one W minus Z0 factor I am keeping aside, and then I am combining Z minus Z0 to the power n and then W minus Z0 to the power n in this object. So therefore this is dominated by this, so M divided by W minus Z0 times this one, right? That is perfectly alright. Now what is W? W runs over CR, right? So therefore W minus Z0, what is this object? This is actually smaller. So that's what I am writing. So this is capital M exactly equal to R. Now what is this object? This object is Z minus Z0 to the power n divided by R to the power n, because W minus Z0 model is R. But then the same thing I am writing, I am saying that look, so this is actually less than M by R, keep as it is. Now what is Z minus Z0? Now Z minus Z0, this is strictly less than, or maybe you can say that this is exactly equal to rho, right? But Z minus Z0, I already told you, this is equal to rho, which is strictly less than R, and which is exactly equal to W minus Z0. Why? Because I have what is called, if I pictorially, this is my CR, this is my CR, this is my what is called, okay. In fact, go back, that will be better. So this is my CR, right? Z is here. So distance between Z and Z0 is less than distance between Z0 and W. That exactly I have done. So distance between Z and Z0, which is exactly equal to rho, which is less than R, which is W minus Z0. So therefore, what is this object? Z minus Z0 divided by W minus Z0. This should be rho by R, and this is strictly less than 1. So maybe you can write this is actually not less than, you can keep this is actually equal to. This is equal to. So therefore, this object dominated by this, which is exactly equal to M by R, keep as it is, and then you have rho by R to the power n. What is your rho? Rho is the absolute of Z minus Z0, and what is your R? R is W minus Z0. But what is the relation between rho and R? Rho is strictly less than R, so that means rho by R is less than 1. That means implies rho by R to the power n, that is also less than 1. So that's what exactly I am writing. So therefore, rho by R is less than 1. Now you see, I will have, this is the term, this is the nth term of my summations. If I take the absolute, this is dominated by some constant, M is constant, R is fixed. So therefore, this is dominated by rho by R to the power n. So therefore, if I take sum n from 0 to infinity here, that means it will have sum. So that means this sum is dominated by M by R, keep as it is, then n from 0 to infinity rho by R to the power n. But what is it? This is Mn test. What is Mn test? So therefore, if I have a series sum over say Anz to the n, if Anz to the power n, which is dominated by some constant times say R to the power n, and if this is 0 to infinity is less or equal to n from 0 to infinity, and this is same as k from n from 0 to infinity R to the power n, and this is finite, then this series what is called converges absolutely or uniformly in the smaller compact set. So therefore by M test, so therefore I will have the summation n from 0 to infinity of the modulus of this nth term, which is dominated by some constant time, then some object to the power n, and since that object rho by R, which is strictly less than 1, that series is convergent series. So therefore by Weierstrass M test, I can say that this series converges uniformly on W runs over CR. Okay, so Weierstrass M test I have already discussed. So this is one of the sufficient criteria to talk about the what is called uniform convergence of my power series. So if you remember, so maybe if I just go back, then it will be clear. I think I have discussed it long before. Yeah, look. So this is my Weierstrass M test. Suppose you have a sequence of non-negative real numbers. So you have a sequence of functions. Now what is here fnz? My fnz is nothing but here. So this is the object. Now f of w z minus z naught to the power n, right, divided by w minus z naught to the power n plus 1. This is the one actually. Okay. And if this is dominated by mn, what is my mn? If you remember, there my mn is nothing but rho by r to the power n. And sum over mn is convergent because rho by r is greater than 1. So that is why. So if this is convergent, then this converges uniformly. So that exactly I have done it. Okay. So that's exactly I have done it. Okay. So therefore this is the nth term of the series. This absolute dominated by some constant time rho by r to the power n. Sum over rho by r to the power n is convergent because rho by r is less than 1. By Wester's theorem say this series converges uniformly and uniformly on CR. CR means W runs over what is called CR. So that means boundary of the circle of center Z0 radius r. So now the series converges uniformly on CR. So therefore if I take the integration in the left hand side, if W runs over CR, then I can push that integrations inside the summation because of uniform convergence. So therefore since this converges uniformly on CR, so therefore look, see, if I take Z, so of course Z minus Z0 is less than R. So because I am considering Z belongs to the what is called interior of CR, interior of CR. So that means I am saying that Z belongs to the set what is called all those Z in C such that W minus Z0 is strictly less than R. Z belongs to that. Okay? Z belongs to that set. So therefore that means what? That means this will implies Z minus Z0 is less than R. That's what I have started with, right? So therefore if I again you just recall the picture. So this is your ball of center Z0 radius capital R. Then I am considering a small ball center Z0 R and I am considering Z is coming from inside that one Z. So therefore if I have absolute of Z minus Z0 is R, then I will already have the expression f of Z. This is 1 by 2 pi I, this is the constant. So now I have an integration in the left hand side of the summation of this series, but I just proved that this series converges uniformly on CR. So therefore I can push the integration inside the summation. So therefore now look, see 2 pi I as it is. So I am pushing the integrations inside the summation. So therefore now integration CR this thing, because I have written this is due to the uniform convergence of my series. So now next part is just to write it. So what is that? This is n from 0 to infinity 1 by twice pi I integration CR. Now you see, so I am saying that since the integrations over W, I am just separating two so variable W and Z. Okay. So therefore integrations f of W divided by W minus Z0 to the power n plus 1 dW keep as it is and just take out Z minus Z0 to the power n out. So therefore this is Z minus Z0 to the power n. So therefore what I will have? I will have some, then I will have this object and then Z minus Z0 to the power n. Now but what is that object? You can easily guess. Because of my function is nice, domain is nice, so therefore by Cauchy's integral formula for nth derivative, this object is nothing but fn z. So what is the Cauchy's integral formula for nth derivative? So if you remember, fn of z0, which is nothing but factorial n divided by twice pi I integration CR f of W divided by W minus Z0 to the power n plus 1 dW. So therefore I will have 1 by 2 pi is there. So therefore 1 by factorial n is missing. So therefore this object is nothing but fn Z0 divided by factorial n times Z minus Z0 to the power n. So therefore this is I am saying that by using Cauchy's integral formula for derivatives. So therefore this is of the form n z to the Z minus Z0 to the power n 0 to infinity n Z minus Z0 to the power n, but what is my n? N is nothing but this one. So this is nothing but the nth derivative of my function f at the point Z0 divided by factorial n. So therefore I can write my f, which is of the form sum over n from 0 to infinity an Z minus Z0 to the power n, where Z minus Z0 absolute is strictly less than R, where small r is less than capital R. So once I have that one, then since R is arbitrary, so therefore in the ball of center Z0 radius R, I will have the expressions of my functions f in terms of power series. Okay. So now it's kind of I'm having the expressions of f around the point Z0 when mod Z minus Z0 is less than R. So therefore, so so that means if I just kind of combining everything in a kind of couple of 1 or 2 sentences. So if I have analytic functions of ball center Z0 radius R, and if I want to write my functions in terms of power series around the point Z0, then what I have to do, you consider this domain ball of center Z0 radius R. Then what you do, you take a small r which is less than capital R, or consider a small open disk of center Z0 on radius small r. Then what you will do, you just first use Cauchy's integral formula, because if I take any point Z which is sitting interior to my circle C suffix small r, that means which is a circle of center z naught area small r, and small r is less than capital R, then I can write my value of the functions at z in terms of the value of the functions on the boundary, that is by Cauchy's integral formula. Once I have Cauchy's integral formula, then in the integrand I will have 1 by w minus z. So I'll have to write that 1 by w minus z in terms of the series expansion or in terms of the powers of z minus z naught to the power n. That I can do that using the fact that since z lies in interior to CR, absolute of z minus z naught, which is dominated strictly less than absolute of w minus z naught, w lies in the circle. So therefore you will have a geometric series expansion, and then to talk, by kind of proving the fact that I have a geometric series, and then that series converges uniformly for all w on C of R, then I can interchange my integrations and summations, and then again by using Cauchy's integral formula for nth derivative, at the end I will have the expressions of my f, which is of the form n from 0 to infinity a n z minus z naught to the power n, where z minus z naught is less than capital R. And what is my an? An is the nth derivative of f at z naught divided by factorial n. This is the uniqueness. Uniqueness is trivial. Suppose you will have the expression of f n z minus z naught to the power n. Suppose you have another series expansion z bn times z minus z naught to the power n, for z minus z naught is less than small r and small r is less than capital R. Then I have to show that a n is equal to bn. But as I said, once I have this power series is exactly equal to f, and this is exactly equal to this power series, so the sum function is same, but I can write a n and b n in terms of the sum functions. So this is a n is equal to this, and as well as b n is equal to also this, so therefore a n is equal to b n for all n. And of course a0 and b0 is, you can just put z is equal to z naught, so only the constant at a naught is equal to b naught is equal to f of z naught, that is perfectly alright. And for other coefficients a n and b n, these two are same, because I can write my coefficients in terms of the sum function, and which is nothing but f n z naught divided by factorial n. So therefore I will have a n is equal to b n for all n. So therefore Taylor series of f around the point z naught is unique, and this completes the proof of the theorem. Okay, so therefore this is very wonderful theorem, and it's a very fine theorem. One of the finest theorem in complex analysis is that if I start with the analytic functions f on some open ball or open disc of center z naught radius r, then I will have a what is called Taylor series expansion or power series expansions of my function shape around the point z naught. Okay, and of course that Taylor series or power series is actually unique. And what machineries I have used to prove that? Just using Cauchy's integral formula or Cauchy's integral formula for nth derivatives, and what is called geometric series expansion of some things. So therefore with these three concepts I have the what is called full proof of what is called Taylor's theorem. Now once I have a Taylor's theorem, now if you remember in my earlier lectures, so let's see can I have the I know the exponential function, like in terms of Euler's the formula I have used what is my exponential functions. Now let's see, I know the exponential functions e to the power z is equal to some, you will have some series expansion, right? Because if I have a series expansion, then exponential function already there. Now since exponential function, it is entire functions, in fact it is analytic everywhere in the complex plane, so therefore in particular it is analytic at 0. So therefore can I have the power series expansion around the point 0, and the exponential expression you know. So let's see how these two things now becomes coincide. So I will have one definitions of exponential function in terms of Euler's formula I will have. Now I will have the expansion like Taylor's theorem or Taylor's series, because if I have analytic functions, then at around that point I will have a what is called Taylor's series. So now let's just combine the series expansion I know for exponential function, whether these two things are coincide or not. So for that, so this is the first example. Find the power series of f of z e to the z around the point z naught is equal to I. Maybe this is kind of one of the problem you can think. What kind of functions f of z is equal to the z? This is an analytic functions, analytic in the entire complex plane, it is an entire functions. So therefore it is in particular what is called analytic at the point I. So therefore just by earlier theorem or Taylor's theorem, it says that around the point I will have a what is called a Taylor series of my functions f around the point I. That means I can write my functions of the form n z minus I to the power n. But what is my n? since I know my sum functions f, I know the expression of n in terms of the nth derivative of f at the point divided by factorial n. So therefore observe that I have functions f of z is equal to e to the z, but what is the derivative of e to the z? E to the z itself. What is the nth derivative? The same e to the z. We have already familiar with this observation. So therefore fn z is equal to e to the power z as it is. So therefore what is fn at the point I, which is e to the power I. So therefore since my function is analytic by Taylor's theorem, it will have a what is called power series expansion around the point z is equal to I, and which is of the form f of z is equal to n from 0 to infinity a n z minus I to the power n, and what is my n, which is fn at the point I divided by factorial n. But since I know my functions f, so I know what is fn I. What is that? This is e to the power I divided by factorial n. So therefore the Taylor series of e to the z around the point z naught is equal to I, which is exactly equal to e to the z e to the power I divided by n factorial times z minus I to the power n. That is one of the way. Now if I take around the point z is equal to 0, then what is that? If I take z is equal to 0, then it is of the form az n from 0 to infinity, then n z to the n, right? What is your n? N is nothing but fn at the point 0 divided by n factorial. But what is fn z, which is e to the z, and what is the value of e to the power 0? This is 1 by factorial n. That means this is 1 by n factorial. So that means you will have the what is called series expansions of your function e to the z, which is z to the n divided by factorial n from 0 to infinity. And you see, that's kind of definitions you are familiar with. In real case, you know e to the power x means it will have a series expansions. Now I have defined my exponential functions in terms of Euler's formula, and then I have kind of discuss that when I will come to the concept of power series, then I will see the series expansion you know and the definitions I have given both are same. Now you see this is same as equal to this one. In fact, more rigorous proof I can give. Okay, so what is the radius of convergence? Of course, its radius of convergence should be infinity because it is analytic everywhere in the complex plane. Okay, so maybe you can say that. So okay, this is one of the way to have the power series of e to the power z, which is exactly equal to z to the power n divided by factorial n sum over n from 0 to infinity. Okay. So this is like Taylor series. So the earlier one, it's the around the point z naught. This is one of the remark I am saying. If f is an entire function, that means it is analytic everywhere in the complex plane. In particular, it is analytic at the point 0. So therefore, I can say that it will have a Taylor series around the point 0. That means I can write fz, which is n from 0 to infinity a n z to the n, where n is equal to fn0 divided by n factorial. Okay. So as I said, so how the exponential functions will have the power series 1 by factorial n z to the n. You see, now this power series, suppose you start with this power series 1 by factorial n z to the power. What is the radius of convergence? By using the formula, you can easily say that. So what is the radius of convergence? Limit n approaches to infinity a n divided by a n plus 1, right? What is that? This is limit n approaches to infinity. What is n? N means 1 by n factorial, then n plus 1 factorial, right? And what is that? This is limit n approaches to infinity, what is called n plus 1, and that is infinity. So therefore, radius of convergence is infinity. That means this power series converges everywhere in the complex plane. So now it will have a sum functions. Let it be the sum function is small f, because it converges everywhere in the complex plane. So I am writing this is the sum function f. I will show that this sum functions f is nothing but e to the power z. What is that? Okay, first of all, that f is an entire function because this power series radius of convergence is infinity. That means it is analytic everywhere in the complex plane. That means my functions f is analytic everywhere in the complex plane, and therefore it is an entire function. This is the first one. Now if I take the derivative, what is the derivative? So if the derivative, I already proved you that the if I have a power series and if I have a sum functions f, if I take the one time derivative of my nth term 1 by factorial n z to the power n, then the corresponding new power series after taking the first derivative of the nth term, then the corresponding sum function is nothing but the derivative of your original sum functions f, the power series you started with. So therefore, if I have the derivative of my functions f, which is the sum functions of the given power series, then which is nothing but the corresponding new power series. That means if I take the first time differentiations of its nth term, that means this is n divided by n factorial times z to the power n minus 1. That means this is nothing but, again you just rewrite it, because this is, if I take the derivative, constant term will vanishes, derivative will be 0. That means it should be n from 1 to infinity n by n factorial z to the power n, which I can rewrite is as 1 by n factorial z to the power n, n start from 0 to infinity, and which is exactly equal to f. So that means what I observe, if I start with this kind of power series 1 by factorial n z to the power n, n from 0 to infinity, first observation is that What is the radius of convergence? Infinity. That means if I have the write the sum functions f which is analytic everywhere in the complex plane, that means it is an entire functions. Now next step is that since it is analytic, then it is infinitely many times differentiable. So that means if I calculate the first derivative, what is the first derivative of your f? It's nothing but the term by term differentiation. So that means I can take the first derivative of each term of my series. So therefore I can have n from 1 to infinity n by n factorial times z to the power n. So therefore if I take the derivative, first derivative of the nth term, because I am talking about the first derivative of the sum function, that I already told you. If I derive this object which is exactly equal to this and which is same as f, so that means the sum functions f has the properties that f prime is equal to f. But I have exponential function c to the z in terms of Euler's formula, and there I know the property that if I take the derivative of my exponential function which is exponential function itself. So therefore one hand I have a function c to the z whose derivative is e to the z itself, and I have another function whose derivative also the function itself. Is there any relations between f and e? So answer is yes, I can do that. What we have to do, you consider this function h of z which is fz divided by e to the z. Now if I calculate the derivative, because f is what? Entire functions, e to the z which is non-zero is an entire functions, cosines of two entire functions, that is also entire functions. So therefore h is an entire function. So if I take the derivative, what is that? This is f prime z divided by e to the z plus f of z, then you will have, or minus e to the power minus z. Okay, you will have it. I am just calculating the derivative. But what is f prime is equal to f? So therefore this is fz by e to the z minus f of z by e to the z. Then I mean this is 0, and this is true for all z in C. So therefore I have f which is an entire functions, I have e to the power z which is also an entire functions. If I consider the function h which is fz divided by e to the z which is also an entire functions, and its derivative is 0 for all z. Now C is very nice domain. So therefore since you have a functions, entire functions or analytic functions or differentiable functions whose derivative vanishes on the full complex plane, your complex plane is nice domain. So therefore your function h has to be constant. So that means you can have f of z which is exactly equal to c times e to the z. But what is the value of f of 0? F of 0 which is nothing but e to the power 0 which is exactly equal to 1. So therefore in that case c is exactly equal to 1. So therefore you can say that f of 0 which is c e to the power 0 which is exactly equal to 1. So that means this is c is equal to f of 0. But what is the value of f of 0? Some function, you can write it. What is f of 0? F of 0 is exactly equal to 1. So therefore this is c is equal to 1. So therefore what functions I am getting? F of z is equal to e to the power z. So this is one of the way to prove that, well, since I know the concept of power series, so if I consider this power series, by looking at the radius of convergence and the earlier theorem, before Taylor's theorem I have proved one theorem. If I have a power series, then the corresponding sum function is analytic in domain of convergence. Then if I take the kth derivative of its nth term, then the new power series will have the same radius of convergence of the given power series. Not only that, if the new power series after taking the kth derivative, if the sum function is g, that sum function is g is nothing but kth derivative of my earlier or the starting sum functions f, that means fk of z is g, that I have already proved. And also you have the relations with the coefficients in terms of the sum functions. So if I use that theorem, using that theorem I can conclude that this power series sum over n from 0 to infinity 1 by factorial n z to the power n, which is exactly equal to my functions e to the power z. So I have written it. So okay, so therefore I can say that e to the power z is exactly equal to this object. So now once I have the series expansion of e to the power z, but I know expansion of sine and cosine in terms of the exponential function, so therefore you have the series expansion of sine and cosines. Maybe I think I should later on I can talk about more on that, but at least the major part of the theorem it is done. Maybe I think in next week or in the week 6 I will talk about that. Once I have a concept of power series, then I know the power series of exponential, which is exactly the series expansion that you are familiar with. But and also since I can write sine and cosine in terms of exponential, then I will also have that series expansion of sine and cosine. And at the end I will show you that, well, the Euler's formula, that means that time when in the initial phase I assume Euler's formula and define exponential, but now I have a series expansions. Now I can have the proper justifications that your Euler's formula e to the power I theta is exactly equal to cosine theta plus I sine theta. Maybe next class I will prove that, and then I will start with what is called Lorentz theorem. I think I should stop here. In my next class I will start with a little bit about more about, I should say, Taylor's theorem, and then I'll come to what is called Lorentz theorem. So I think I should stop here. Thank you.